Imagine, for a moment, an alien world hidden beneath the familiar blue, not on a distant planet, but right here, on Earth. It's a place where the rules of life, as we know them, bend and break under unimaginable pressure and profound toxicity. We're talking about the deep ocean's deadly brine pools, liquid graves lying thousands of meters below the surface, each a unique, isolated experiment in extremophile survival. Today, we're plunging into these abyssal anomalies, comparing their terrifying beauty and profound scientific implications, to uncover the secrets they hold about life's tenacity and perhaps, its origins. Prepare to descend into the abyss, where lakes of poison shimmer in eternal night. Our journey begins deep within the Gulf of Mexico, home to perhaps the most infamous of these abyssal anomalies, the Jacuzzi of Despair. Discovered in 2015 by the remotely operated vehicle Hercules, this particular brine pool sits at a staggering depth of 3,300 meters, or nearly 11,000 feet. Imagine a seabed depression, almost perfectly circular, roughly 30 meters wide and 3.6 meters deep, filled not with seawater, but with a supersaline, oxygen-depleted concoction. Its brine is over 5 times salter than the surrounding ocean, with a salinity reaching around 200 parts per thousand, compared to normal seawater's 35 parts per thousand. The water temperature here is also surprisingly high, a balmy 19 degrees Celsius, 66 degrees Fahrenheit, while the surrounding deep ocean hovers just above freezing. This lethal combination creates a dense, inescapable trap. Anything that ventures into the jacuzzi, crabs, fish, even entire microbial communities, perishes almost instantly, preserved in a macabre tableau of death, leaving behind perfectly intact skeletons and carapaces. The boundaries are shockingly sharp, like an invisible shore where life abruptly ends, a shimmering mirage of liquid death. This pool's formation is attributed to subsurface salt tectonics, where ancient salt deposits, remnants of the Jurassic era when the Gulf was a shallow sea, are dissolved by geological activity, seeping upwards to form these concentrated death traps on the seafloor. But not all brine pools are created equal, and our next stop takes us to a starkly different, yet equally deadly, comparison, the brine pools of the Red Sea. Here, the genesis of these toxic lakes is often linked to hydrothermal activity, rather than dissolving evaporites alone. Take, for instance, the Atlantis II Deep, discovered in the late 1960s. Located at depths exceeding 2,000 meters, this is not just a brine pool, it's a vast sub-basin, containing several distinct layers of superheated, metal-rich brine. The salinity here can reach 257 parts per thousand, even higher than the Gulf of Mexico pools, but the temperature is truly mind-boggling, soaring to 68 degrees Celsius, 154 degrees Fahrenheit, at its deepest point. This heat is generated by magma chambers close to the seafloor, actively venting superheated, mineral-laden fluids. What truly sets the Red Sea brine pools apart, beyond their extreme heat, is their incredibly high concentration of heavy metals, iron, manganese, copper, zinc, which precipitate out, forming vast, commercially valuable ore deposits on the seafloor. While the Gulf of Mexico pools are primarily defined by their immense salinity and anoxia, the Red Sea pools add intense heat and extreme metallicity to their lethal cocktail, creating an even more potent barrier to conventional life. These are not merely toxic lakes, they are boiling, metallic cauldrons, continuously cooking up new geological formations and challenging our understanding of hydrothermal systems. The sheer lethality of these underwater lakes begs a crucial question: can anything truly survive here? The answer, surprisingly, is yes, but not in the way you might imagine. Within the absolute core of the most extreme brine pools, macroscopic life is utterly impossible. Fish, crabs, even robust invertebrates, instantly succumb to osmotic shock, their cells rupturing under the extreme salinity, or their respiratory systems failing in the anoxic, sometimes superheated, environment. They become the fossilized victims we've seen. However, the boundaries of these pools, where the normal seawater meets the toxic brine, host a fascinating struggle for existence. Here, unique microbial mats, often vibrant with color, flourish. These are extremophiles, single-celled organisms that have evolved astonishing adaptations. Some are chemosynthetic, deriving energy not from sunlight, which never penetrates these depths, but from chemical reactions involving methane, hydrogen sulfide, and other compounds found in the brine. They perform an incredible feat, thriving on the very chemicals that are poisonous to most life. Surrounding the pools, a diverse community of deep-sea fauna often thrives, drawn to the chemosynthetic productivity at the edges, like deep-sea mussels and tube worms, forming oases of life around these zones of death. This comparison highlights a critical point. While the pools themselves are biological deserts for macrolife, their interfaces are often teeming with specialized microbial and invertebrate activity, making them hotspots for unique biological discovery. So, what have these comparisons revealed about the deep ocean's deadly lakes? On one hand, we have the Gulf of Mexico pools, often formed by dissolving ancient salt deposits, characterized by extreme salinity and anoxia, creating distinct kill zones where organisms are dramatically preserved. On the other, the Red Sea brine pools, born from active hydrothermal venting, adding intense heat and concentrated heavy metals to the mix, pushing the boundaries of chemical and thermal tolerance. Both are deadly, yet both are sources of incredible scientific insight. The surprising conclusion, however, extends far beyond Earth's oceans. These abyssal brine pools, these isolated worlds of extreme chemistry, temperature, and pressure, offer us tangible terrestrial analogues for environments we might find on other planets and moons. Take Europa, Jupiter's ice moon, or Enceladus, Saturn's moon, both believed to harbor vast subsurface oceans under ice shells. Scientists theorize that these extraterrestrial oceans could contain hydrothermal vents or dissolving salt deposits, potentially forming their own versions of brine pools. Studying Earth's brine pools, understanding the limits of life within them, and observing the chemosynthetic ecosystems they foster, provides invaluable clues in the search for extraterrestrial life. If life can find a way to thrive at the edges of a boiling, metal-rich, supersaline lake in Earth's abyss, what incredible forms might exist in similar, alien conditions light years away? These deep-sea death traps are, paradoxically, laboratories for understanding life's most fundamental principles. These mesmerizing, yet utterly hostile, environments force us to confront the very definition of life itself. They are stark reminders that our planet still holds countless secrets, challenging our perceptions of what is possible. The deep ocean, with its hidden lakes of poison, is not merely a vast expanse of water, it is a dynamic, constantly evolving frontier, a realm of extremes where nature experiments with chemistry and biology on a grand scale. Every discovery pushes the boundaries of our knowledge, painting a more complex, more astonishing picture of Earth and, by extension, the universe. What other unseen wonders, what other deadly beauty, awaits us in the unexplored depths? The journey into the deep ocean is far from over, and with every new technological advancement, every new dive, we uncover another piece of this profound puzzle. If you're as fascinated by these hidden worlds as we are, hit that like button, subscribe for more deep ocean mysteries, and share your thoughts in the comments below. What do you think is the most surprising aspect of these deadly lakes? Until next time, keep exploring the unknown.